Hi everyone, welcome back to the video series on chapter Magnetism and Matter. We have been discussing a lot on the second subtopic matter. In the last video, I have talked about diamagnetism. If you haven't checked that video, please go into the video link and clear your doubts. So in today's video lecture, I'll be talking in detail the second type of magnetic materials or magnetic substance, that is your paramagnetism or paramagnetic substances. Alright, before I dig into the detailed concept of paramagnetism, I would like you to look at this too. What I'm doing out here is the comparison between your diamagnetic substance and your para. Since para we haven't started yet, but what I want you to know for now is, see this guy, magnetic susceptibility, which I have also talked in my previous video, was your negative. So if a magnetic susceptibility is negative for a substance, it is considered to be diamagnetic in nature. And for para, keep in mind it is supposed to be positive, but not that higher positive value, but just positive. Alright, the second point I would like to compare is dia is your weak phenomena. Also, para is your weak phenomena. But what is weak? In both the cases, this is weakly repelled, whereas on the other hand, para is your weakly attracted, or you can say it is magnetized. Number 3 point I would like to compare is, if this is your magnet and if I hung a diamagnetic substance, it's going to repel. Or if I take a para substance, in the same experiment I perform, I hang it, it's going to get attracted. So we can say the magnetic material, this paramagnetic substances, is now rotated from weaker magnetic field zone to the higher magnetic field. Alright, now let's continue in detail what this paramagnetism is and what it comprises basically. Alright, so one point I forgot to compare over there is dia was something to do with your subatomic level, whereas para is something to do with your atomic level. You can say an atom or an ion or a molecule is involved or is participated in the process of magnetization. Now the key point you should keep in mind is, in paramagnetic substances, they already has a permanent dipole moment. This is interesting. They already have this permanent dipole moment, but they are randomly oriented before magnetization, and what happens is, during magnetization, these dipoles will be aligned in the direction of your applied magnetic field. Alright, before I apply the external magnetic field and see how the dipoles are oriented, I would like to explain why this permanent dipole moment exists in the atom. Okay, so the concept of permanent dipole moment is seen when you are taking the atoms whose outermost shells have a valence electron. Okay, it's something to do with your valence electron. For example, I am taking aluminum 13. Its atomic number and the electronic configuration we can write as 2, 8, 3, right? 2 plus 8, 10, plus 3, 13. Okay, so let me first fill up this electrons in a shell. So as we know that first shell, K shell, can only have 2 electrons, and the subshell would be your S shell. So here 2 electrons are placed like this, and this is your first 1s, first shell completed. Now let's talk about this 8 electrons. So second shell has your 2s. Okay, 1 electron. But before I fill up the second, it will have other vacant spaces like this. So this is nothing but your 2p shells, and it has 3 chambers. Now let's fill the 8 electrons here. So already 1 is here, 1, this is 2, 3, 4. Now five, 6, 7, 8. So this electrons also done. Now we are remained with the 3 electrons. Now this is your third cell. Again, it will have a cell in the third electronic configuration, and you are going to have your p cell also, and more chambers are opening. Here is your D shell, so SP and D also comes here. This is your 3p and 3D. Alright, so 3 electrons go like this. 1, 2, and this, okay, let me change the color, the third electron. Now this electron will contribute in your magnetization. So this will be acting as your permanent dipole moment, and they may be randomly oriented. So what happens is, the moment the external field is applied, let me denote it by B naught, these magnetic moments gets aligned in the direction of your applied magnetic field. Okay, before this magnetic field line is absent, what's going to happen is, if you have a bar of paramagnetic substance, over here the dipoles or the atoms are random. Okay, and also the permanent dipole moments are randomly oriented. Now the moment I apply this external field, all these dipoles are going to align in that particular direction of your applied magnetic field. Alright, why I call this paramagnetic as weak phenomena is because the atoms are always in thermal motion. So if you don't know what it is, it's actually therm means your heat motion. So because of thermal motions, the atoms are never as stationary, they are never fixed. Okay, so if you increase more heat to a parasubstance, the atoms are more, if you apply heat to these parasubstances, the atoms are going to vigorously move here and there. So if you don't know, I'm going to in more detail the basic concept. The thermal motions could be of 3 types depending upon the matter. As we know, we have 3 states of matter: solid, liquid, and gas. So we are having motion of rotational motion. Number first point, translational, vibrational. Okay, so vibration is basically seen for your solid atoms. Alright, solid, because they are closely packed and the atoms cannot move freely, so what they do is they just vibrate in their mean position. Whereas if you look into this translational or rotational motion, this both is seen, either one of them is seen in your liquid or gas, because simple reason, the molecules are a bit far away as compared to your solid. Now, because of these thermal motions, this magnetic phenomena is not seen. What we have to do is we have to lower down the temperature so that in such a way, if I would like to draw the atoms how it is viewing after I lower down the temperature is, they would be now showing less motion. It's not like they are completely stopped, but they are not showing the random motion, and they are now settled down, kind of settled down. And here we can see individual magnetic permanent dipole moments are aligning in the direction of your externally applied magnetic field. Okay, so this is the reason why I said it's a weak phenomena. Let's discuss the examples. Oxygen at STP. In last video also I discussed what this STP is: standard temperature and pressure. So standard temperature is your 0 degrees Celsius and pressure would be 1 atmospheric pressure. So next is your aluminium, sodium, calcium, and copper chloride, CuCl. Okay, so if you look at this individual atom, or this molecule, you're going to always see that they have a valence unpaired electrons, and they would be having your permanent dipole moment, which contributes in your magnetization. Now this phenomena will only last when the source is there, the applied magnetic field is there. The moment you disconnect it, the phenomena will stop. That is, the dipole orientation would be random again. Okay, experimentally it has been found that capital M, which is your magnetization, is directly proportional to your applied magnetic field upon the absolute temperature. Okay, so I have just written the scalar quantity, not the vector one. So magnetization is directly proportional to your applied magnetic field upon your absolute temperature. Okay, so this is not an equation. For equation, there has to be an equal to sign. So I can write this as M equals B naught by T, B naught upon T. So I cannot just write equal to sign after replacing this proportional sign. I should be introducing a constant. So this constant out here is your C. So capital C is nothing but your Curie constant. See, whenever you see T or temperature, absolute temperature in an equation, this Curie constant is going to appear. Actually, this Curie, if I tell you, this equation was been introduced by Curie. So C is your Curie constant. This equation was introduced by Curie. This equation can be further understood like this. If I increase B naught, since B naught is directly proportional to magnetization, more number of magnetic dipoles are going to orient in the direction of magnetic field. So this is first case. Another is, so this magnetization is inversely proportional to your absolute temperature. Now, if you decrease the temperature, what happens is you are ceasing the thermal motions, the atoms are coming closer and closer, and more number of dipoles are easily magnetized. They are reoriented, they are redirected in the direction of magnetic field. So with these two cases, we can reach this MS state. What is this MS state? This is the saturation state. Now, saturation is a point where all of the permanent dipole moments are aligned in the direction of magnetic fields, and there are no further magnetic dipoles, permanent dipoles left for orientation. So there reaches the saturation point. Okay, so let's name this as equation number 1. This equation can be further simplified in terms of your chi magnetic susceptibility. So we know this another term. What do we know? That B is equals mu H. Okay, I'll be discussing in another video how I derived this equation, this is actually your magnetic field and this is your magnetic intensity. So how this relationship we have obtained, I'll be deriving in the next video. For now, just let's take this example, this equation. All right, if here mu further is your mu naught R, your relative permeability, and mu naught. Permittivity is free space. Permeability in free space. So if I just write B naught, because I've mentioned out over here the external field to be B naught will be your mu naught and H. Okay, this is equation number 2. Okay, so I'll be discussing this thing in detail in the next video when I derive this and I reach to this equation. For now, I would like to help you what this H is. As I said, it's your magnetic intensity. It's a vector field. Okay, so this magnetic intensity, how this term comes is actually you're going to take a solenoid. Okay, actually solenoid is nothing but a coil having n number of turns, and you're going to insert these materials, either your dia or para or ferro. So I'm taking this paramagnetic substances as our topic is today's topic is this. I'm going to insert the paramagnetic substance in this solenoid, and now what I do is increase the current in the solenoid. So that is how the magnetic intensity H terms, when we say that the interior field of the solenoid is enhanced or increased. So that is how H has been introduced there. That's how H has been introduced. That is, if you increase the current, the magnetic intensity will increase, or vice versa, decrease, and it's going to decrease. Now, using 2 in 1, I can write M as C mu naught H upon T, equation number 3. Alright, I want you to know there's another thing. Again, this we'll be deriving soon. You should know this. So this M can also be defined in terms of H. I'll be discussing in the next video how this relationship is coming, but for now just remember this. M, magnetization, is your chi into H, where chi is, as you know now, it's magnetic susceptibility. Alright, I can replace this chi H in terms of M, that is putting 4 in equation 3. The left hand side can be replaced as chi H C by T. Now this H are on the numerator and equal in both the sides, so I can cancel them as like this, and what remains is T. So this is nothing but your Curie temperature. So this Curie temperature is very, very important in examination point of view. I hope you have understood today's video. If you have any question, please feel free to ask in the comment section below. So this was me, Martha, your physics tutor. Hope to see you in the next video. Before I go, I would like you to answer me this maybe in comment section below. if this is your paramagnetic substance and I take the magnetic field lines, so my question here is why maximum field lines are inside this substance, or in other words, why the magnetic field's intensity, or in other words, why the magnetic field is enhanced inside the paramagnetic substance. So see you soon with yet another video series on ferromagnetism, equally important for competitive exam point of view. So stay tuned. Bye bye.